All right, so let's get started. Hello everyone, thanks for being here. Today we have Fatemeh Tabatabaei, who's originally from Iran, where she graduated at the University of Tehran. But it was for a short time, because then she quickly came to Europe, Germany, where she did his thesis in Bonn. And soon after that, after her studies, she moved to Heidelberg with a DFG grant to work in a group of Eva Schinnerer on different aspects of the ISM and star formation and the relationship with the magnetic fields and so on, which is exactly what she's going to tell us today. She's a generic postdoc, and she's one of the few in this institute, I think, that knows a lot about ISM. There are not so many, actually, working on ISM and the relationship by the magnetic fields and so on. So,
thank you very much, Justus. So, as you know, the stars, as the fundamental building blocks of the galaxies, are formed in the dense clouds of the gas and dust, and enrich the ISM with the heavy elements with magnetic field, with high energy particles, which could actually affect the subsequent formation of the stars. And during various star formation mechanisms, there would be various kind of emission from radio to X-rays and even gamma rays in the star forming regions, like what we see here in the LMC Magellanic Cloud, so strong gamma ray emission. So this kind of star formation feedback is important because could actually suppress the subsequent star formation by removing the gas from the surrounding region in the star forming regions via the strong winds like the cosmic ray driven winds. And then after the massive cluster is formed, we don't have any more gas here to form further stars. On the other hand, star formation feedback could be positive, so it can trigger and enhance the star formation. As what we see, there are some stars forming in the superbubble shells of the supernovae remnants. So, in principle, the interplay between the stars and the ISM could be very important because it could change the structure of the galaxy, and it could redistribute the gas in the disk. It could cause the outflows in the disk, like what we see here in M82. And in order to understand better the structure formation in the universe, the evolution of the galaxies, then it is important to know about this interplay. So, after giving an introduction about the ISM, I will mainly focus on the dusty ISM and the non-thermal ISM, which has not been studied in detail, and then I will come back to the energy balance in the ISM and the important factor for the structure formation. So, as you know, gas is the most important component of the ISM in terms of the mass. So here, for example, we see the ISM, the gaseous ISM in the Andromeda galaxy, different phases, atomic traced by H1, molecular trace in CO, and the ionized gas H alpha. So these could be similar or non-similar in some parts of the galaxy. And it's also another component is the dust, which is almost 1% of the gas mass, but is important for the formation of the molecular cloud, for the formation of the CO, H2, and also for the formation of the stars. So the most important component of the ISM in terms of the energy density is the mostly neglected ones, the relativistic particles and the magnetic fields. So the cosmic ray protons can be traced and observed in gamma rays, electrons, radio synchrotron, for instance, and magnetic field, again, radio synchrotron. As I show here, this is a synchrotron emission from the Andromeda galaxy. So, and also there are also other methods, polarization in dust, enzyme, and splitting. So, first of all, we should know how these various ISM components are interconnected. Well, we know that gas and dust are mixed. But how they are mixed exactly, with which phases of the gas this mixing is better? Is it ionized? Is it atomic, molecular, neutral? Which one? Still some details are unknown. But in general, we see that, for example, in the Andromeda galaxy, there is a good correspondence between the dust column and the contours of the molecular gas. So a linear relation between the atomic gas and the dust optical depth at H alpha wavelength, which is proportional to the dust column, exists. But on the other hand, the molecular gas is proportional to the square of the dust column. So such kind of condition is actually needed to have a kind of balance between the formation and destruction of the H2. So now it's well proved that gas and magnetic fields are coupled, but this is mostly the molecular phase of the gas, the neutral, the molecular gas, as is seen in the this kind of relation in the for the Milky Way clouds actually holds for the densities higher than what we start to see the molecular gas. So, but how we can explain this? This is only understandable if the gas everywhere is partially ionized. So then what we can say about the, so is it exactly the same everywhere? And what's the minimum degree of ionization in order to have such kind of coupling? So the gas and cosmic rays are related in the way that when cosmic rays interact with the gas, they ionize the gas and they produce the gamma rays. So it's a kind of aggressive relation. So it's nicely shown by the Fermi-Lat observations that we have a bright gamma ray emission in the galactic plane where we have the concentration of the molecular gas. And but now, what about the star formation and the relation between these ISM components? So, most of our knowledge is about the star formation and the gas relation. Their surface density are related following a power law relation with an index n. So this is the Kennecotte-Schmidt law. So this index, according to the theories, is going to be determine the mechanism which actually regulate the star formation in galaxies, and hence it could be different case by case. So Bigel et al. Found a kind of linear relation between the molecular gas and the star formation surface density. But on the other hand, if we also include the atomic gas, the relation would be superlinear. So this kind of linearity between the molecular gas and star formation surface density we also found in M31 at better resolution of 200 parsec, and but you see that the scatter is higher. So this means that the Kennecotte-Schmidt law is getting to be break down on a small scale. So what is this scale? And if this scale is universal, if it is the same in different galaxies, is still an open question. So about the dust and star formation, most of our knowledge is that the stars are heated by the dust is heated by the stars, and they produce the IR infrared emission, and hence the infrared emission is a good tracer of the star formation. As we see, for example, here for a bunch of H2 regions in M33, there is a linear relation between the star formation surface density and the 100 micron infrared emission. And it's the same as if we get the galaxies or H2 regions. So it's the same relation exist for the galaxies and H2 regions. But the question is that what about the physics of the dust grain in star-forming regions and non-star-forming regions? So are they sensitive to the environmental effects? And what would be the role of different phases of the star formation in the change of the grain physical properties? This we don't know. And about the cosmic rays, we know that, okay, this supernovae explosion and supernova remnant are actually the sources of cosmic ray electrons and cosmic ray protons as well. But we don't know about the acceleration regime, injection index, and about the other mechanisms which could be also in the giant star-forming regions if the injection index getting to be changed, and we don't know anything about the details of this relation. And still, in general, we don't have a kind of observational evidence for various cooling mechanisms of the cosmic ray electrons. So, about the magnetic field in star formation is even worse. Most of the thing that we have is is just based on the theories. So there is a small-scale dynamo theory which says that the magnetic field could could be amplified by the turbulence and compression due to the massive star formation activities. But actually, we don't have any observational confirmation for that. So, the most important question is that, so what's the role of magnetic field in the feedback, in the star formation feedback, and also other kind of field like the agent feedback? We don't know anything. Also in the star formation quenching. So this needs to have kind of high resolution, multi-scale, multi-wavelength studies in nearby galaxies, which are optimized between the having high resolution and no distance ambiguity. So we are going to study this, pursuing our main goals, which are like this: how do those physical properties change in different environments, and what's the role of the star formation, and also to understand the magnetized ISM and to investigate if there is any kind of connection with the star formation, and what's the role of magnetic field in the energy balance in galaxies in general. So we perform a kind of a state-of-the-art observations by observing both space-based and also ground-based telescopes from radio to optical. And now first I focus on the dusty part of the ISM based on these studies. The Herschel data actually brought us lots of detailed information about the dust emission and the physics of the dust. So as I showed you in the Science Day, so the M33 dust study, the global dust study of the M33 can be explained by a double modified black body emission, as it's written here, the formula with the index, which is wavelength dependency of the dust of 1.5. You know that the standard value is 2, which is the Milky Way value, and is confirmed by the Planck observations as well now. But here for M33 in general is 1.5. And I've also found that both the colder and warmer dust components actually get colder toward the outer parts of the galaxy, which is expected as the radiation field decreases toward the outer part. But then this nice Spire data actually has a good potential to give us much more information about the spiral structure of the M33. So you see this for the first time we uncovered these folliculant structure, these narrow dust lanes in between the spiral arms. And it seems that apart from that there is a kind of diffuse extended disk in M33. So we tried to separate the diffuse disk from the spiral arms in Ziluris et al. 2012 work, and we found that about 30% of the total dust luminosity comes from the extended disk, and also assuming that the beta is fixed, the emissivity index is fixed, 1.5 across the galaxy, we separated the role of the cold and warm dust in these contributions. But then the question is that does it really the case that the beta is fixed across the galaxy? So don't we expect that the wavelength dependency of the dust changes with the environment? We know that beta actually is representative of the grain dust physical properties like the structure, grain size distribution, and also the chemical composition. And all of these characteristics are subject to change due to the variations like destructive processes, constructive processes, destructive processes like shattering, sputtering due to the shocks, or constructive processes like the condensation of molecules onto grains, or coagulation when in the cold dense cores when the stars are formed. So as these processes all belong to different phases of the star formation, and as the star formation is not uniformly distributed across the disk, then we would expect a kind of contrast, a kind of variation of the beta as well. So we would expect to see a kind of arm interarm contrast or inner outer disk contrast in beta. So we are going to map the dust physical properties including the beta, so dust temperature, mass, and beta for a two-component dust model, taking into account that we have 5 data sets from 70 to 500 micron, and we have the unknowns to temperature and to mass surface density for each dust component and the beta. So we are not going to use the chi-squared usual chi-squared method, because it's proven that this method actually injects some artificial correlations and some kind of degeneracies between the beta and temperature. So instead of that, we are going to solve the equations. We have 5 equations corresponding to 5 wavelengths, and we could have actually 5 unknowns when we are going to solve the equations. Then this is possible if we assume that the cold and warm dust emissivity indexes are the same, or if because the most of the mass resides, dust mass resides in its colder phase, we attribute the variable beta to the colder dust and fix the warm beta to some values, but we select different values and we try these Newton-Raphson method to solve the nonlinear system of equations pixel by pixel. So for each approach shown here, we perform a kind of Monte Carlo simulation to study the systematic effects of the approaches, and we first generate sets of physical parameters, random parameters in this range of variation, which is wider than the reality, and then we get it as input parameter, and then we derive the synthesized intensities, and then we use the synthesized intensities as the observed intensities, and derive the Newton-Raphson method, derive the output parameters by applying the Newton-Raphson. So the ideal approach is the one which leads to output equal to input, and here we got that this case beta warm equal to 2 and beta cold variable is the best case with least effect of the systematics. So, and here is the result of this approach. So we have the maps of the cold dust surface density or cold dust mass and the warm dust mass, or the distribution of the dust you can call it. So the cold dust follows the speculent spiral structure, and but the warm dust is very clumpy in the central region. It's very bright in the central region, and immediately we can recognize these giant H2 regions here. And interestingly, we see that both the warm and cold dust densities are higher in these H2 regions, indicating that still there is lots of fuel for the star formation in these massive star forming regions. So here I show the H-alpha map and the warm dust map. You can compare it. So by eye, that they are very, very similar, and we could actually see, we could follow these H2 regions in the dust map as well. So actually, somehow we were able to create the H-alpha map just using this the dust information. If you don't believe on your eyes, here is the quantitative correlation of these two maps. So you see that the linear correlation exists with these outliers, which comes from the systematic of the method. So, and here are the dust temperature maps. So both of the cold and warm dust are higher in the inner parts, and they decrease toward the outer parts. And you may say that, okay, they are correlated, but no, it's not the case. They are not correlated, which is actually in agreement with our previous guess that it could be two different independent heating sources of the dust, one from the young massive stars and the other from the interstellar radiation field. And the other point is that our method does not inject a kind of artificial correlation. So this is the most wanted map, the beta emissivity index map. So you see that it's not fixed, it's not constant, there is variations, and it's higher in the inner disk, and its value is something between 1.7 to 2 or higher than 1.5. It's very similar to the Milky Way value, but in the outer parts is less than 1.5, and there is a radial decrease towards the outer parts, which is similar to what we have for the metallicity in M33. And on the other hand, we see that there is a correlation between the beta and the star formation rate traced by the H-alpha emission. That's interesting because it can already show us the feedback, star formation feedback in the ISM, because young massive stars inject the higher heavy elements and higher metallicity in the ISM, for which we have the steeper spectrum or larger beta emissivity index. So we can detail this here in this cartoon. So if you remember, the H-alpha was mostly concentrated here, the H2 regions, the young massive H2 regions. So this is the inner 4 kiloparsec, and for that, but the older in the outer parts, we are dominated mostly by the older stars. And then we know that for silicate beta is equal to 2 from the theory, and for carbons is equal to 1. And then this actually fits to our what we got from the our beta map. So a steeper beta in the inner and flatter in the outer parts. Also, you can attribute these to the different grain size distribution, because in the outer parts the ISM is more diffuse, and in the diffuse ISM it's been shown that the grains are smaller, and for the smaller grain size we have flatter beta. So this also has been observed in the Milky Way, in our own galaxy, by the Planck group collaboration group. So there is this inner outer disk contrast. So now, what about the non-thermal ISM? So as I said earlier, we can trace the non-thermal emission using the having the synchrotron emission, which is produced by spiraling relativistic particles along the magnetic field. So it is linearly polarized, and it follows a kind of power law relation with an index which is unknown, but people mostly take it as a fixed parameter again. So based on this synchrotron emission, we can derive information about the cosmic ray distribution and also the magnetic field. But the reality is not that simple. What we observe is a mixture of the synchrotron and the thermal emission. So this is the what we observe is the radio continuum emission. And in order to understand the non-thermal ISM, we first have to separate the thermal contribution. So as I said, traditionally people assume a constant index, synchrotron spectral index, but this is not realistic, especially when we are going to map the synchrotron structure and the thermal emission as well, because the cosmic ray electrons actually suffer various energy loss mechanisms when they interact with various physical conditions in the environment, like ionization, Bremsstrahlung, adiabatic synchrotron losses, and inverse Compton scattering. So we developed a thermal non-thermal separation method based on a thermal radio template. So here it is the thermal emission and an ionized gas. So kind of based on a good tracer of the ionized gas, we can do this, assuming that the ionization and recombination are balanced. So one of the recombination lines could do that. So the perfect is the radio recombination line because it's not extincted. But the point is that these lines are usually weak and observationally impractical. But on the other hand, H alpha is strong, but it suffers from the extinction. So some people also use the infrared emission as a thermal radio template, but this is tricky because you know that also the non-thermal mechanism could cause the infrared emission. So what we did was just use the infrared emission information to get some information about the dust distribution, and then correct the H alpha emission for the extinction and with de-redden the H alpha. So here is the result of the thermal non-thermal separation for M33. So these points showing the H2 regions, star forming regions, and so this is the thermal emission. Synchrotron emission appears like kind of patchy, extended structure, but still is stronger close to these star forming regions. And if I show you the case of the Andromeda, it's also similar. So the thermal emission following the H alpha, following the H2 regions. Also we have some diffuse emission at the center, bright nucleus. Synchrotron emission is also bright in the center, but we have a kind of thick ring in synchrotron, and it still is brighter close to the these star forming regions. So this actually shows that the synchrotron emission is a good tracer of star formation as well. This was already indicated indirectly by the radio IR correlation, and our study, our kind of result study and separation of the thermal and non-thermal emission actually leads to more consequences for the result radio IR correlation, and we can actually uncover the physics behind the radio IR correlation, and this is the thing that we are going to discuss in this UAS special session, and you are all invited to this meeting. So this is an interesting case in GC6946, which we have lots of giant H2 regions, and it's very strong in the magnetic field. There are strong magnetic field which appear not in the in the optical spiral arms, but in between the optical spiral arms, where we don't have anything. But it's not true actually. It's filled with the diffuse synchrotron emission, meaning that there are intense synchrotron energy loss along the magnetic field. So if this is true, we should expect a kind of steep synchrotron spectral index along these magnetic arms. Is it the case? Yes, we can look at it because now we have the non-thermal map at 2 radio wavelength, 20 centimeter, 3 centimeter, and we can derive the non-thermal spectral index. We can map it, and again we see that It's not fixed. It has variations, it has local variations, and yes, it is steeper along these magnetic arms. So on the average, the mean synchrotron spectral index is 0.8, and we get a kind of one for the non-thermal spectral index here, which is the typical value for the synchrotron cooling. And it's interesting to see that these star-forming regions appear to be green here, which having the kind of flat non-thermal spectral index, or something like 0.6, which is indicative from the supernovae activities and the injection of the cosmic ray electrons. So similar in M33, another galaxy. So we have flatter synchrotron index of 0.6 in these star-forming regions, and steeper toward the outer part in between the spiral arms. So now what we can say altogether is that the non-thermal spectral index shows the local variations. Now what if we can, how we can see this kind of effect or feedback effect of the star formation in the global kind of studies? Is it possible to trace such kind of flattening of the non-thermal spectral index globally? So here is the kingfish sample, which covers a wide range of various galactic characteristics, like the morphology. We have dwarfs, we have ellipticals, we have spirals, and also star formation and metallicity. So this is the kingfish sample of galaxies. So recently we have observed this sample in radio at 3 centimeters, 6 centimeters, and 20 centimeters in order to study the radio acidity of this sample. And we changed the name of the kingfish to kingfisher, which means kingfish in radio, which is the name of a bird. And now for this bird, we find that the non-thermal spectral index indeed decreases with the star formation surface density. And so the integrated energy index of cosmic ray electrons in galaxies actually decreases with the rate of star formation. Or we can say that the cosmic ray electron population gets younger and more energetic if the galaxy has higher star formation activity, which is logic. So such kind of things is for the first time. So far people had thought the synchrotron spectral index is fixed, 0.8. So now what about the magnetic field? So we can actually get information about the magnetic. We can measure the magnetic field in radio using the polarized, using the Q and U Stokes parameters, polarization data we have. So first of all, the magnetic field usually is categorized into two different groups, two different kinds, the ordered field and the turbulent field. And so the ordered field is kind of large scale field, which can have a kind of regular or ordered structure, and the turbulent is random and isotropic distribution. So the ordered component of the magnetic field can be obtained if we have the polarized intensity, which is doable if we have the Q and U. And with PAA polarization angle, we can actually see what's the order of these vectors. So you see here the ordered magnetic field distribution in M51, and you see that it nicely follows the optical spiral arms. But this is not always the case. In case of M33, the ordered magnetic field still follows the spiral pattern, but this kind of spiral distribution does not have anything to do with the optical spiral pattern. So there is no correlation or anti-correlation between these two spirals. So when we have the polarized intensity, it's also possible to derive the turbulent magnetic field strength by subtracting the polarized intensity from the total synchrotron emission. And here we mapped it for M33 and 6946. So in both galaxies, we see that the turbulent magnetic field strength is higher in the inner parts. And in the case of 6946, because we have better resolution, we could even see that a stronger magnetic field are found in the giant H2 regions. So for this one, we can go further and see about the magnetic field, star formation rate, surface density, and what we find is that there is no correlation between the ordered field and the star formation rate, but the turbulent field and the star formation are correlated, and at the end the total field and the star formation are correlated as well, but following a shallower dependency, meaning that because the turbulent field is stronger than the ordered field, so it's mostly due to the turbulent field and the star formation, which hints to the dynamo theory in which we have the amplification of the magnetic field due to the star formation activity of the turbulent field. So for the Kingfisher, for our galaxy sample, we also find that similar correlation exists between B and sigma and star formation rate, meaning that the galaxies having more star formation rate actually are more magnetized, or they have a stronger magnetic field. So this actually could hint to the fact that the Star-Wars galaxies actually show kind of feedback effect from the star formation, so they show less star formation than expected. Starburst galaxy. So this is obtained based on the gas amount in these galaxies. So why is that? They refer to the actually star formation feedback, and now we see that there is a correlation between the magnetic field and star formation itself, meaning that magnetic field could be much more stronger in the starburst galaxies, and then this is the connection of the magnetic field and feedback. So magnetic field could actually prohibit the formation of the stars when it is coupled with the gas. So now that we have some information about the non-thermal ISM, we can go further and study the structure formation in the sub-galactic scales by just studying the energy balance and comparing different energies. We have the thermal energy density, the quantity that usually people refer to. We have now turbulent energy density. We have now magnetic field energy density as well, and we can just perform such kind of comparisons. So first, we see about the thermal energy density in M33 at 500 parsec radial beams. So there is a slow decrease with the radius toward the outer parts of the thermal energy density get weaker. So what about the turbulent? So the turbulent energy density is higher by one order of magnitude than the thermal energy density, which could indicate that the ISM that we are looking at M33 is like low beta plasma, and it is as we have it in the Milky Way as well. So what about the magnetic field? So magnetic field energy density also appears to be similar to the turbulent energy density, and is higher than the thermal energy density again, and this could indicate that the ISM is actually dominated by the supersonic magnetohydrodynamic turbulence. So what about the NGC 6946? So this is also the case for this galaxy. The total magnetic field, the same quantity that I was showing you in M33 also dominates here when we compare with the other energy densities. So these two are ionized and neutral molecular and ionized contribution to the thermal energy density, and this is the regular magnetic field, and this is the turbulence. So even the magnetic field energy density appears to be stronger than the turbulent energy density in this galaxy. So is this due to the stronger ordered magnetic field in this galaxy that we have such kind of behavior? Still, we don't know. So as a summary of my talk here, we found that the synchrotron emission is not only a kind of shallow, smooth distribution across the galaxy as it was obtained previously using the traditional separation method. It's clumpy. Again, it's brighter, close to the star-forming regions, which indicate that there is amplification of the turbulent magnetic field, there is injection of the cosmic ray electrons in the star-forming regions. And for the cosmic ray electrons themselves, we find that the star formation actually makes the energy of the cosmic ray electrons higher, which is expected. So this was only based on the theory. Now we actually present observational evidence for that. Actually we have later spectral indexes of the synchrotron emission in the star-forming regions proved both locally and globally. But on the other hand, for the different cooling mechanisms in the ISM, still we would need high resolution data. So regarding the magnetic field in the star formation, we found some observational evidence that the star formation is amplified in the star forming region, that magnetic field amplified in the star forming regions. But on the other hand, there is no correlation with the large scale magnetic field in the star formation. And the point is that we should not neglect the magnetic field. Actually, it could be very important. We should compare with the turbulent energy density and in the energy balance in the ISM, even in normal galaxies. So we are going to perform cloud scale resolution studies of the ISM in M33 using our EVLA survey at 4 to 7 gigahertz and 1 to 2 gigahertz. We have performed 25 mosaics at C band, 12 mosaics at L band, so for which we would have cubes of the continuum data. And it's not only the Stokes time, but also QUV to the polarization as well. So we can actually find the topology of the magnetic field in the molecular cloud and star-forming regions, and we can see we can actually say something, or we can actually say something about the star formation theories. If it is the turbulence or magnetic field which is important for the star formation, we can decide on this later, and also the energy balance on a smaller scales. So as another project that I'm going to do here is to investigate the role of bars in the central gas mass concentration in the galaxies. So we have something like 20 galaxies for which we have the apex submillimeter data, and we can actually trace the gas mass using the coal dust, because the dust is a good tracer of the dark gas, is proven, and so we can actually study the star formation efficiency in the center of these galaxies, if the bar actually suffers the star formation in the nuclei or not, and also the sort of studies that we have done here, the feedback studies in the star forming region, would actually be extended to AGNs and supermassive black holes, where we have where the feedback effect is much more stronger actually. And here, for instance, This is for the case of NGC 1097. So we can study the energy balance in this star-forming ring. So here observing optical dust, 25 micron, and these contours, these are the H2 data. So we have different phases of the ISM, the data of different phases of the ISM. We have the radio data as well, so we can have a kind of complete study of what's going on here between this star-forming ring and this area, and then here this nucleus. So that's it, and thank you.
Questions? I have a question for you. You show us the connection of the magnetic fields. You first showed the magnetic fields are widely spread in these paragalaxies, right? And I was wondering whether these magnetic fields have any influence on the dynamics of the system, on large scale, or is only localized on small scales?
No, on large scale, that's a good question. Actually, should study that. I mean, we don't know. Some people say that Batanar, I don't know if you know him.
Yes, I remember some talks from Eduardo Bataner and so on. That's why I'm bringing up this.
But I don't believe that. But anyway, we should study this. We have the data here, and we can compare it with the various kind of dynamical information that we have, and we can actually address your question. Yes, that's a nice question.
Yes.
Yeah, I was seeing that, as you explained, there is a correlation between the magnetic field, the turbulent component, and the star-forming regions. I'm surprised, or are you surprised that there is no relation between the star-forming regions and the magnetic field, the total flux? Because I will understand that the turbulence is enhanced, but there is no connection between the star-forming regions and the magnetic field.
You mean
flux.
physically or?
The non-turbulent one. You say that the turbulent component is enhanced and there is a correlation,
Yes.
but no with the total magnetic.
Yes, there is.
Oh, with the total.
as
Okay,
well.
I was
Yes,
understanding there was.
So the first one, the upper part is the total magnetic field, and here is the turbulent one. So there is a correlation with the total and star formation as well. But there is no correlation with the ordered magnetic field. So here I just shifted the total and the ordered just for a better illustration. So.
So I had a question on the starburst galaxies, on massive starburst. You said that magnetic fields could enhance the star formation, the other way,
Suppress.
negative feedback, suppress. All right, but only in very massive starburst, because it's here, or in
Not
any.
only, but there could have a strong effect because it's strong. So we could see also here the effect in the feedback in the molecular clouds, for example, but not actually in this. The thing that I have shown you, because the resolution was not that enough to go to those details actually. So I will tell you later when we studied the EVLA data. We reduced the EVLA data first, and then we analyzed this EVLA data. Then I will answer your question.
No questions?
So the proportionality between the turbulent field and the star formation rate might implies a cause. So is the cause from star formation to turbulent field, or from turbulent field to star formation?
Yes, it could be also other way around. We don't know. So this is something that again we would need kind of resolution for that. So what we see here is a correlation between these two quantities. But what causes what? We have only one theoretical thing that if we assume that there is canonical Schmidt law and there is equipartition between magnetic field and cosmic rays, we would have this exponent between the star formation rate and the magnetic field strength. This is similar to what we have now, and because of that, I'm saying that it's most probably due to the amplification of the magnetic field because of the star formation. But if it is really true or not, we would need higher resolution data or higher resolution analysis. Actually, we can address this starting from the molecular clouds. We should trace the magnetic field in the molecular clouds. If it is getting to be dominated by the turbulence or the magnetic field, then it would be deterministic if the magnetic field has something to do with the formation of stars or no, or if it is turbulence. So this would bring the answer to your question. So.
Questions? No? Mike.
It was just a comment, really. I mean, have you thought about trying to do this study for something like the Large Magellanic Cloud? Because there you would have the spatial resolution to look at some of these issues, right? I guess it depends where your telescopes are. But
No, I have not done this because other people are supposed to do that.
Ah, okay.
But Large Magellanic Cloud is interesting because the magnetic field is weak there.
Okay.
Dwarfs, the magnetic field gets weaker. And hence, studying that and detecting it, it's more difficult, of course.
Mm-hmm.
So M33 is really an ideal case.
Okay. Mm-hmm.
More questions? No? So let's thank Fatemeh again.